So 12.5 and 12.6, I'm going to do it the same way we've been doing the last couple sections. We're going to review the big ideas on the board first, and then we're going to practice the problems, okay? So if you're making a theorem sheet and you started that last class period, I would get that out. We're going to add to it today. Can somebody tell me who started a theorem sheet what number we're on? 11. So we've done 11, or this is 11? This is 12. Okay, so the 12th thing we're going to learn in chapter 12. And I'm going to kind of go through the notes as we learn them, but we're going to skip all the examples. So first of all, 12.5 is all about angle relationships. I need to review two things with you real quick. You've already learned if it is a central angle, its vertex is at the center. What's the relationship between the angle and the arc? It's the same. They're equal, right? The angle equals the arc. You've also already learned last class period that if it's an inscribed angle, its vertex is on the circle. What's the relationship between the angle and the arc? Okay, the angle is equal to half the arc. Everybody agree? The first thing today is really not different than that last thing we just wrote on the board. The only difference is the definition for an inscribed angle said that not only is the vertex on the circle, but the sides had to be chords. This angle here on the board is not an inscribed angle because it is made up of part of a secant which contains a chord, and this is a what? Tangent. So by definition, it's not really an inscribed angle. But where is its vertex? On the circle. So it has the exact same relationship. So the way I think about it is where is my vertex? If my vertex is at the center, the angle equals the arc. If my vertex is on the circle, the angle is half of the arc. So the first thing today is really the same as what we learned last class period. If you have an angle, even if it's not an inscribed angle, but its vertex is on the circle, then the angle is equal to half of the arc. Just be careful. When we're talking about the arc would go all the way from this point A all the way around to the vertex. Does that make sense? Okay, so that's the first thing today. Questions? Is equal to half of the arc. No, because then it wouldn't be tangent. If you change this angle, it would then become a secant, and it has it would be half of this arc. What's up? Sorry, say it again. So moved this down, then it would no longer be, I don't think you, like once it hits this point, it can't, I mean, it would either be, I don't know how to explain that. If this is just touching at this point. So if it's just touching at this point and this line touches this circle down, if I made it more obtuse, I don't know how to, I mean, it's either, I don't know how to describe that to you, Jonah. So if it goes out further this way, it's still half of this. I mean, it wouldn't be touching at that point then, I guess. It would have to be a different point. I don't know how to say that. Like if I have a circle here, so you're saying if I go like this, man, I don't know how to explain that. Let me think about it. I'll come back to the end of the class if I come up with a better way. I see what you're trying to say. I can't come up with a good way right this moment off the top of my head, okay? But I will. I'll come back to you. Other questions? All right. We're going to move ahead. And while I'm having you work on some problems, I'll look at Jonah's question. So here is the next theorem for today. There's only 3 theorems in this section, okay? You guys back with me? So the 13th thing in chapter 12 that you need to know is what happens if your vertex is not at the center, it is not on the circle, but it's somewhere else in or outside the circle. So this is what happens if your angle is inside the circle, but it is not at the center. Okay, so again, I just ask myself, where's my vertex? Is it at the center? Is it on the circle? Or is it inside the circle, but not at the center? So for example, I'm going to label these points A, B, D, E, and F. This theorem says if your angle is inside the circle, so we could be talking about angle 1, angle 2, angle 3, or angle 4, any of the angles. I'm going to look at angle 1 here, which would be angle ABD. The measure of angle ABD, according to this theorem, is it will be half the measure of the 2 arcs added together. And the 2 arcs it's talking about are the 2 arcs that that angle creates. So if you look at this angle, the arc that it creates is what arc? Say it again. AD. So the measure of arc AD plus, I'm going to call it the vertical arc, but be careful, it is not congruent. So maybe you just want to think of it as the arc that's across from it. So what's the other arc that would be created across from that one? EF. These 2 arcs are not necessarily the same measure, but you're going to add those 2 arcs, so AD plus EF, and then you're going to take a half. So the rule is if it's inside, it is half the sum of the 2 arcs. Add the 2 arcs and take a half. Questions there? Okay, if I were looking at angle FBD, what 2 arcs would I add? FBD, this angle, which 2 arcs would I add? FD and EA, and then take a half. Okay? The last one for this section, I'll come over on this side of the board since I'm running out of room. Right, that's if it's on the circle. If your vertex is on the circle. Nope, that's what this rule is. We haven't learned anything else. So there's 3 rules we've learned so far. If it's at the center, it's equal to the arc. If it's on the circle, it's half the arc. And if it's inside but not at the center, you have to add the 2 arcs and take a half. Okay? And the last one for this section, number 14, is what happens when it is outside the circle. So now we're looking at an angle like here. And again, does not have to go through the center. It could go through the center. If you're looking at your notes, skip ahead to this part here. What are the 2 red lines here? What kind of lines do we have? What is this called in chapter 12? A secant, part of a secant, and this is tangent. This would be 2 tangents, and this would be 2 secants. And so it does not matter what you have there if the angle is outside the circle. So notice angles 1, 2, and 3 are all outside the circle. The rule is similar to if it's inside, but the difference is going to be you'll take a half and subtract the 2 arcs. So if it is outside the circle, again, I'm talking about the vertex. Where's the vertex? If it's outside the circle, you're going to take half and subtract the 2 arcs. So for example, in our problem, the measure of angle DAF would equal 1/2 of What are the two arcs that that angle creates? So when we're talking about the arcs, I need to maybe be more specific. It's the arcs that are inside the angle, or the one across from it if it's inside. What are the arcs that are inside this angle? DF and BE. Be very careful that you subtract the bigger one minus the smaller one. You shouldn't be getting negative answers. So it's the bigger one minus the smaller one. So it'd be the measure of arc DF minus the measure of arc BE. So if it's outside the circle, it's half the difference of the two arcs. The bigger one minus the smaller one. Okay? Everything's a half unless it's a central angle. If it's central, they're equal. If it's on, it's half the arc because it only creates one arc. If it's inside, it's half the arc and the one that's vertical to it added together. And if it's outside, it's half the arc and the one across from it, but you subtract their measures. Questions on the 4 rules for today about angles? All right, I want you to take some time and try to work through some of the examples. So we'll start at the beginning. I'm going to give you about 10 minutes or so. Let's see how far you get. Don't understand. Don't be shy. And the rest of you, if you do understand, be kind. Don't be rude to someone who asks a question. Okay, back to the beginning here. First answer, first problem should have been 65 degrees. Anybody need me to go over how the first one was 65 degrees? Okay, going on to the next one. The answer should have been 116 degrees. This one was a little harder for the last class. Anybody need me to go over this one? Yes, okay. So there's a couple of different ways you could work this problem. To me, the easiest way to work the problem, and I'm going to cover up all of that, is to say I'm looking for arc GF. And so I ask myself, what angle creates that arc? Meaning, if I were to connect this point F and this point G to make an angle, what angle made that arc? What angle is that arc inside of? So that would be this angle FG, and then they don't have a letter here. I'll put D just so we can talk about it. So FGD is the angle that makes this arc. If this angle is 122 degrees and this is a straight line, what's the measure of this angle? 58 degrees, because they have to be supplementary. What kind of angles did we learn these two angles are called that form a straight line? Heard somebody say it? Linear pair. So this is 58 degrees. If this angle is 58 degrees, we learned that if the vertex is on the circle, the angle is half the arc. So if the angle is equal to half of the arc, and the angle is 58 degrees, what do we need to do to find the arc? Multiply by 2. So we would multiply both sides by 2. The 2 and the 1/2 cancel. 2 times 58 is where they got 116 degrees. Questions on that one? Anybody do it a different way? Okay. Go into the next one. This one should have been 126 degrees for angle AEB. Does anybody need me to explain this one? Again, please don't hesitate if you do. 126. And if you haven't gotten to it, that's fine. We can work it too. So maybe if you didn't get that far. Anybody? Okay, moving on. The next ones. A should have been 40 degrees and B should have been 63 degrees. Does anybody need me to work one of those or both? A or B or both? I hope you're being honest. Anybody? Okay, moving on. So then there's this question. What did you guys get for the answer for FKH? 48? Okay. The answer should have been 48 degrees. Does anybody need me to work this one? Okay, next one. What did you get for the measure of ACB? 45? That's correct. Does anybody need me to work this one? Okay, moving on. Did anybody figure out the measure of arc YZ? Martin? 90? Jonah? 164? Anybody else? How many people got 90? How many people got 164? So how many people are not sure what the answer to this question is? Raise your hand. All right. Okay, so we're going to go through and work this question. The answer is 164. Let's go through, sorry Martin, let's go through and work it together though. A couple of different things you could do here, but this is a hard one. And they're going to get hard. You're going to have to look at it and go, man, I don't know what to do. And when you don't know what to do, just start finding things. Find anything you can find until you see something in the picture that goes, oh, that's what I can do. So think about vertical angles. Think about linear pairs. Think about if it's an angle outside or inside. What's our rule today? So just anything you can find. So Jonah, do you want to help us maybe think about what you did? Mm-hmm. You mean supplement? Uh-huh, yes. So you found this angle was 67 degrees because these two angles form a linear pair. Everybody with Jonah there? Okay. Okay, can you hold on one second while I go through that? You are correct, and I want to write it down for everybody. So first of all, does everybody notice and understand why Jonah said this is 67, so this is 67? Okay, so when we look at that 67-degree angle, is that at the center, on the circle, inside the circle, or outside the circle? Inside. So what Jonah said is he wrote an angle, or an equation that said the angle is equal to half of the arc plus the arc. That's our rule, right? If it is inside, it is 1/2 arc plus arc. So he plugged in the measurements that he knew. What is the measure of the arc that's inside this angle? 67 is the angle. What's the arc? 68. And the vertical arc, or the arc across from it, would be the one that he's looking for, which is UY. Does everybody follow that? I would write this down so you have this example. So 67 is going to go in for the angle, equals 1/2 of, the first arc was 68, and the other arc that we didn't know was UY. So he's going to find arc UY. Everybody okay with that? Plugging in what we know, looking for what we don't know. Questions so far? Okay, what do you want to do to solve for UY? We could distribute. If we distribute, be careful that you distribute it to both. What else could you do instead of distributing? Multiply by 2 and just get rid of that fraction. Either way, I would probably multiply by 2 just because I don't like to work with fractions unless I have to. But I'll go ahead and do that this time since that's the first thing we thought. Half of 68 is 34. Just make sure you distribute the 1/2 over here too, so it's half of the measure of arc UY. Subtract 34, and you end up with 33 equals 1/2 the measure of arc UY. And so then we need to multiply both sides by 2. So what's the measure of arc UY? 66 degrees. Are you guys with me? Okay, so Jonah found this arc right here, UY, to be 66 degrees. Right, Jonah? Okay, then what did you do? Okay, I'm going to switch to a different color. So what he noticed then, maybe I am, there we go, is he's looking at this arc, YZ, that's created by that outside angle 49 degrees. Does everybody see how YZ is created by the 49-degree angle? So he's going to use this outside angle and this rule. the outside angle should equal half of arc minus arc. And he now knows this outside angle is 49, so that equals 1/2 of, make sure you do big arc minus little arc. What's the bigger arc? The YZ, the one we don't know. So we'll put measure of arc YZ minus, and what's the smaller arc? 66, the one that he found. Questions at this point? Okay, and then now we need to solve. Do you want to distribute the 1/2 or multiply by 2? Okay, so we'll multiply both sides by 2 to get rid of the 1/2. Just remember when you do that on the right, those just cancel. So we have 98 equals the measure of arc YZ minus 66, and so then we add 66. And is that 164? Yes. So we find the measure of arc YZ is 164 degrees. And they will be that hard. You are going to have to think, what can I find? How can I find it? So what I always ask myself is, I look at what I'm trying to find, if it's an arc, and say, what angle makes it? So trace back and find your angle that's making that arc. And then say, do I have enough information using one of my rules? If not, start finding something else you can find in the picture until you work your way there. Any questions? All right, did we go through all the examples or were there more? That was it? Okay, so look at the board. Do you see the extra example over here on the board? Extra example. Okay, I'm going to give you about 2 or 3 minutes. I want you to see if you can find X. Add this to your notes. You will see it on your homework. You will see it on your test. So it's a 42-degree angle. You're looking for arc X. And those are tangents. The Zach's theorem. That's right. I like it. Zach's theorem. Okay, 12:6. Are we ready to shift gears and talk about line segments? Yes. Here we go. Quickly. Quickly. Back to your theorems page if you're making a theorems page. We are on number 15? 15. This section is all about segments. I want to make sure we're clear that we're talking about line segments, not angle measures. So we're going to use these same ideas of where do the lines intersect. Do they intersect inside or outside? But we're talking about the segments now, not the actual angle measures. So we're going to be trying to find the lengths of chords or the lengths of parts of chords or parts of secants. We're going to go through and look at, there's 3 theorems in this section. But first, some vocabulary. So I'm going to ignore that. First theorem, and then we'll talk about the vocab. First theorem is what happens if your chords intersect inside the circle. Does everybody see that those are 2 chords intersecting inside the circle? Okay, so what we want to figure out is if 2 chords intersect inside the circle but not at the center. Now think about it. If they intersected at the center, what would these pieces be? What would these pieces all be? Radii. And what would be true about all of the radii? They're all the same. But in this situation, they're going to ask you to figure out maybe what's the length of the green piece or the blue piece or the purple piece or the red piece. They're not radii because they're not at the center. So here's the rule. 15th theorem for chapter 12. First one in this section. If the lines intersect inside the circle, but not at the center. then I'm going to call this, just to make it easier to work, AB, and I'll call this circle O, C, D. The rule is part of one chord times the other part of the same chord equals part of the second chord times the other part. So I'll say part times part equals part times part, or look at the picture. Look at one chord. It's going to be A times B is going to equal, look at the next chord, C times D. Okay? If they intersect inside the circle, to find one of your parts, it's just part times part equals part times part. But it has to be from the same chord. So part times part on one chord equals part times part on the other chord. Questions? Okay, moving on. Skip some examples. We'll come back to these. Some of these are hard. Vocabulary before we learn the last one here. By the way, I said there's 3 because we already learned 1. One of the relationships with segments was if you have 2 tangents. What did we learn about AB and AC? Before Zach's theorem, because Zach's theorem has to do with angle measures and arcs, what did we learn about the tangents, the segments? Come on, talk to me, guys. What did we learn about AC and AB? They're congruent. They're the same. Okay, so we already learned that. That's the first thing about segments. Here's the second thing about segments. Now we're going to talk about the third thing, and then that's the end of the big ideas. We need to know what is a secant segment and what is an external secant segment, and they're going to ask you on the homework to identify these things, so this is important. We already know a secant is a line with arrows that goes through the circle and touches twice. A secant segment is going to be a part of the secant with at least one endpoint on the circle. So a part of the secant with at least one endpoint on the circle. So that would mean that PM would be a part of the secant. NM would be a part of the secant. Looking at the other one, KM would be a part of the secant. JM would be a part of the secant. What would we call PN and KJ? Chords. And then they're going to talk about external secant segments. The external secant segment is the part that lands outside the circle. So all of these are secant segments, but the ones that are outside the circle are NM and JM. Does that make sense? Okay. So secant segment is just part of a secant. Part of the secant could be the chord, or it could be the other PM or NM. Okay, here's your last theorem here. Number 16. Now what happens if those lines intersect outside the circle? It could be you have 2 secant segments. It could be that you have a secant and a tangent. It could be that you have 2 tangents, which we already know. Either way, it's going to be the same rule. Here's the rule. It is whole times outer part equals the whole times the outer part. Woe equals woe. Okay? By whole, this is what I mean. Be very careful. This is where students make a mistake. So I'm going to label this. This is A, B, C, D. Okay, what is the whole secant segment? Careful, that would be multiplying the 2 segments. What's the whole secant segment there? A plus B. Every year students make a mistake when this is a 2 and this is an X. What do you think they put for the length of that segment? 2X. It's not 2X. What is it? 2 plus X. So be very careful. If this is A and this is B, the whole thing is A plus B. What's the outer part? B. So the equation here would be A plus B times B equals, what's the whole thing here? C plus D, and what's the outer part? D. Everybody with me? If they intersect outside the circle, so inside, part times part equals part times part. If they intersect outside the circle, we're talking about the line segments now, not the angles, but where do the line segments intersect? Outside the circle. It's a little different here in what it turns out to be in your work, but it's the same rule. Jonah? Mm-hmm. No. Mm-hmm. Huh? We'll look at some examples. But yeah, they don't have to be congruent. You could have a chord that's really tiny here intersecting a very long chord here. This part times this part should equal this part times this part. Okay? But we'll look at some examples. Okay, look at this one here. Are we good? Did that confuse you? Okay, where am I confusing you? Okay, we'll look at some examples, but the rule is this part times the other part should equal this part times its other part. Okay, those do not have to be congruent chords for that to be true. Any two chords, if they intersect inside the circle, their parts multiplied should equal the other parts multiplied. Okay? Back up to here. Everybody look at this example. This catches people sometimes. If this is A, this is B, and this is C. Elijah, you with me? Okay, what's the whole part here? A plus B. What's the outer part? Louder? B. That should equal, what's the whole part here? C. What's the outer part? C. So what's C times C? C squared. They write it as a separate rule in your notes, but it's not really needed as a separate rule. It's still just whole times outer equals whole times outer. It's just that the outer part is the whole part. So it turns out to be that part squared. Does that make sense? Okay, so in your notes, you're probably going to see that as a separate rule here, but I'm not writing it as a separate rule. It is just this rule. If they're outside the circle, it's whole times outer equals whole times outer, but sometimes the whole thing could be the outer part. Skip something there. Okay, and the only vocab word I skipped there was tangent segment. So look in your notes here and make sure that you understand a tangent segment is just a part of your tangent, where at least one endpoint is on the circle, just like a secant segment is part of a secant with one endpoint on the circle. So A, B, and AC are tangent segments, and we already learned that they're congruent. Questions? Let's try some problems. I think that's all that should be in your notes as far as, yes. So let's go back. And let's work some problems. We're going to do it together here. So first example. Where do the lines intersect? Inside or outside? Inside. So what's the rule? Part times part equals part times part. So pick one chord, GH. What are its two parts? 14 and X. So 14 times X should equal. Now go to the other chord. What are its two parts? 10 and 7. So 14 times X should equal 10 times 7. Okay, we're multiplying them, not adding them, so that's why they don't have to be congruent. 2 times 4 is 16. 2 times 4 is 8, but 4, never mind, that didn't work. 2 times 8 is 16, and 4 times 4 is 16, and so notice those are different measurements, but they still give us the same product. So we're saying that they have to multiply to be equal, not add to be equal. So that may have been where some confusion was about the segments having to be equal. All right, what do I do here to solve? 14x equals 70, and then to solve for x. And so x is equal to 5. And it just said find x, but it also said to find what else? The length of each chord. What are the chords in this picture? GH and EF. You have to list them if it says find the length of each chord as well. EF is easy. What is EF? 17. GH, you had to find x to answer. If x is 5, what is GH? 19. Do not put line segments above them. You are giving me the distance. Questions on the first example? Okay, go on to the next one. We're going to skip this one for a minute, come back to it. It's the hardest one. So go on to this one. Find the value of x and the length of each secant segment. So first of all, where do they intersect? Inside or outside? Outside. What's the rule? Whole times outer equals whole times outer. Okay? Whoa equals whoa. Whole times outer equals whole times outer. So be careful. What's the whole thing here from E to G? 8 plus x. Again, biggest mistake I see is students writing 8x. It's not 8 times x, it's 8 plus x. So 8 plus x times, what's the outer part? 8 equals, what's the whole thing on ED? What's the whole thing on ED? 16. 9 plus 7, 16. And what's the outer part? 7. Okay, let's work the problem. What do we need to do? Distribute, thank you. 8 times 8 is 64. 8 times x is 8x. 64 plus 8x equals, what's 16 times 7? 112. Subtract 64. And 8x is equal to 48. Divide by 8, and what is x? 6. Be careful, that's x. The directions said find x and find the length of each secant segment. So what is the secant segment that we don't know the measurements for here? Okay, back to our vocabulary. Make sure you're clear. A secant segment has to have one endpoint on the circle. So GE would be a secant segment. And then we don't need to name this secant segment because they already told us it was 8, right? So we just need the ones we don't know. So GE, how much is GE now? 14. I'm hearing somebody whisper it. 14. 6 plus 8. We don't need to name this secant segment. It's already given to be 7. But what is ED, the other secant segment? 16. So you have to list both secant segments. You do not need to list the chords. Those are not secant segments. Those are chords. Okay? Any questions? Okay, keep going. Is this the last one? Okay, and then we skipped one. All right, where is it intersecting? Inside or outside? Outside. This time I'm going to call on you because some of you are way too quiet. What is my rule? Let's go with Ethan. If they intersect outside, what do I do? Multiply what times what? Okay, more specific. We don't multiply ML and LK. So look up here for our rule. If they intersect outside the circle, you take the whole secant segment times the outer part of that secant segment and set it equal to the other secant segment's whole part times its outer part. Okay, so now look at your picture. Look at one secant segment. So I'll look at just this one. What's the whole thing? 20. So we'll do 20 times, what's the outer part? 5 equals, now go to the other secant segment. What's the whole thing? X. And what's the outer part? X. And remember, this is the one where it's a tangent, actually, not a secant, tangent segment. So it looks like a different rule, but it's really not. It just turns out to be x times x. What is x times x? X squared. And what should this equal? 100. Now somebody tell me what the answer is. And that is wrong. What is the answer for x? It is not just 10. Plus or minus. This is the one that a lot of students miss every single year, and it's going to kill your Algebra 2 grade if you do not get it clear. When you have an x squared, what kind of function has x squared in it? It's not linear. What kind of function is x squared? Quadratic. And quadratics always have how many solutions? 2. Always. The first thing Ms. Siegert or whoever your Algebra 2 teacher is might ask you next year is, what is a quadratic? And every year her students stare at her with blank faces. They have no idea what quadratics are. You learned them in Algebra 1, and we have done them all year long in here. Quadratics have the highest exponent of 2. The highest degree is 2. And how many solutions does every quadratic have? 2. Sometimes they're the same solution, sometimes they're different solutions, but there's 2. When you take the square root, you have to remember to put plus or minus 10. If you just put 10, you will be wrong in Algebra 2. But can x be negative 10 for our geometry question? No. So the answer is just 10. Okay? But be careful, because in Algebra 2, you can't just put 10 unless it's an actual picture of something, and it can't be a negative. Okay, we skipped one problem. Let's go back to it. It's the hardest one. Let's see how smart you are. By the way, first of all, let me point out that 8 is referring to this segment here. Okay? Let's read the question. The art department is contracted to construct a wooden moon for a play. One of the artists creates a sketch of what it needs to look like by drawing a chord and its perpendicular bisector. So what's the length of the chord in the picture? 18. So 18, the chord's the dashed line. And then they've drawn in the perpendicular bisector of this chord. Right? This is perpendicular and it's bisecting the chord. And we learned they don't even have to tell us it's bisecting it. We learned if it's perpendicular, it's going to bisect it. It says find the diameter of the circle that would be used to draw the outer edge of the moon. Is this point the center of the circle? No. So they're looking for the diameter, which has to go through this somewhere, all the way, so that if you were to keep drawing this circle, that would be the diameter. That's terrible. Okay, so let's think about it. Remember the theorem we learned that said if a piece is perpendicular to a chord and it bisects the chord, that piece has to be a part of the what? If this is perpendicular and bisecting the chord, what does this have to be a part of? It's in 12:1, first things we learned. What does this have to be a part of if it's bisecting the chord and it's perpendicular to the chord? The diameter. Has to be a part of the diameter, could be the radius, could be a part of the diameter. So we know the diameter has to go all the way across through here. Okay, I need some suggestions on what you think we should do here to solve. There's 2 different ways we could work this problem. What do you think we could do? What are some things you notice? What would these lengths be? What would these lengths be? 9. Okay. 9 and 9. Any other suggestions? Looking to see if they tell us. They don't say anything about that. Maybe that. Actually, I think I lied to you. That 8 inches is supposed to be, and that's not a very good representation. This should be this whole length here. Okay, now suggestions. Should make it a lot easier based on what we just learned today. Think about what we just learned today. Complete your circle. What could we do? Jonah? Any diameter of the circle, they're all the same. We're looking for the diameter. No, there's not 2 circles. There are some arcs. Oh, I'm sorry. If you were to draw a circle for the inner part of the moon, there would be a circle, but this says find the diameter of the circle used to draw the outer edge of the moon. So it's the circle that I've created going around that outer edge. So you're looking for the diameter of that circle. You guys are making this way harder than it is. Use what we learned today. No, because it's not the center. This is not the center of the circle. They never tell us that. This circle, and this is just a chord in that circle. It is not necessarily going through the center. Christian? Exactly. Hey guys, where do the 2 lines intersect in your circle? Inside or outside? Inside. Part times part equals part times part. Look at one chord. What are the 2 parts of this one chord? 9 and 9. So 9 times 9 should equal. What are the 2 parts in this other chord? Something and 8. So it should be 8 times x. Part times part equals part times part. What does that give us for x? 81 equals 8x. Divide by 8. What is x? 10 point what? Okay, 10 and 1/8 or 10.125. That's x. Is that the diameter? No. What is the diameter? 18.125. Add your x and your 8. So 18.125. Units? Inches. Okay, we made that way too hard. Way too hard.